So example 5. Oops. So this is continued. So this would be the third page. So in this one here we want to work out the rotation. So let's take the beam again. So that's the real system. And we've got our UDL on it. And our UDL is a magnitude Q. And as we said before, there's going to be a rotation there and an identical rotation there. So let's do what we did before, and let's draw the bending moment diagram, which we know is going to be a parabola, and we know that the maximum value of the parabola is going to be QL squared over 8. So this time we want to, we decide that we're going to ignore the shear deformations in calculating our rotation, because we're going to assume it's going to be a reasonably sized beam. So ignoring shear deformation makes our life easier in the virtual system. So you will note that I didn't plot the shear force diagram this time, and this time we're going to apply a 1 kilonewton meter. So I'll put my bar on top to show that it's a virtual moment. And of course in this virtual system there's going to be no deflection, so I've not shown the deflection of the virtual beam. So bending moment diagram. So let's draw the bending moment diagram of this beam. So we could draw like there, and showing the arrow on the side. So if you wanted to, that's 1 kilonewton meter. And obviously at the other end of the beam it's going to be 0. So let's work out this rotation. So the rotation theta is going to be equal, multiply that by the 1 kilonewton meter for dimensional accuracy, but most people would just ignore that and not bother to write that out, because we know it's all going to cancel each other out. This time we're going to have to integrate between 0 and L, because we can't use symmetry, and we can't use symmetry because the bending moment diagram on the virtual side is not symmetrical, so we're going to have to do integration from 0 to L. So it's m as a function of x, m bar as a function of x, and divide all that by EI. So let's just take out the 1 over EI on the outside and just show what it is that we have to integrate. So the m bar is going to be the whole bending moment diagram of magnitude QL squared over 8, and that needs to be multiplied by the value at the center, because that's going to be the centroid of the parabola, would be around, the centroid of the area is going to be where the cross is, and so if we read that off and get that value there, then the magnitude of that value there is nothing more than half, because that value is going to be 1, and that 1 comes from there. So we've already got half the problem. The other bit is now to work out the area of the parabola. So going back to Appendix 2, there's a diagram there parabola, and then it's got the area is equal to length times height over n plus 1. So we know that n is 2 because it's a parabola, and therefore it's going to be 3. So the length in this case here is going to be L over 2. Yeah, I think you've got to say that it's going to be L over 2. So the length of the parabola is going to be L over 2, and then the height of the parabola is going to be QL squared over 8. And of course, because the parabola looks something like that, it's only one side that this equation has given me, so this area is only of that side there. So the area of that, where that is that, has to be equal to 2 times, because it's going to be 2 of these, it's going to be that side and that side. So 2 times L over 2 times the height QL squared over 8, all divided by 3. So the 2's disappear, and you get QL cubed over 24. So let me just check that. Yeah, it's QL3 over 24. So back to the area of the parabola, it's the length times the height times n, when n is 2, so obviously I should have put a 2 there, and then divided by n plus 1, which is going to be 3, so that's going to be multiplied by 2, so we're going to get QL cubed over 24 multiplied by 2. So the value of that at centroid of parabolas, or because it's going to be there, so as we've said, it's going to be that value there, which is going to be a half. So therefore, going back up here, we get 1 over EI times what we've just calculated, which is going to be QL cubed over 24 times 2 times 1 over 2. So the 1 over 2 comes from that value there, and the QL cubed over 24 times QL cubed times 2 over 24 is obviously all of that bit there, and then that comes out, let's just put my thetas there, so theta is equal to 1 over EI times QL cubed over 24. So that tells you what that rotation up there is, and by symmetry it's also what that rotation there is, because those two thetas are going to be the same. So you can see that the 1 bar up here has disappeared because it's just 1, which is why we apply a unit load so that the 1's can disappear. So from there we can see we can get an equation for theta, which would be the rotation at the end of the beam.